Your brother tell you what? So how do you where was it? PWM. How do you use PWM to control the output? Rise time, false time. Seriously? Do you agree? How do you use PWM to control the output voltage of your converter, DC-DC converter? Okay, next. Change the duty cycle, yeah? Okay. I hope everything comes back, because there's a 1 week recess, yeah? Alright? Okay? I'm refreshing your memory. So in this course, in the part 2, my aim is not to teach you anything. I'm not going to teach you anything. Okay? Anything new. Alright? My aim is to do the same thing with what you did in part 1, but do it in a modern way using a microcontroller. What you did in part 1 was you use an op-amp to build the so-called controller, error amplifier, compensator, these terms. Now, in part 2, we use a microcontroller to do this. Understand? Okay. And then the objective of this course, again, is not to teach you anything. So, you understand every word there, right? Yes? In this course, I assume you have some idea. You have taken a first course in Introduction and Feedback Control. Even if you have not taken it, you have some idea about what feedback is about. Right? Okay? So you understand what is a closed loop control system. You understand what is an open loop test. Yes? Yes? Yes, huh? Okay? So the objective of this course is to introduce to you a key component, those key components needed in implementing a microcontroller-based system. Later on, we'll go into the details. And the second bullet point is the most important one, to let the student has a first-hand experience in doing this kind of things. All right? I always say, maybe your brother will tell you. Did your brother tell you? Okay, I will say, so this course, I'm not teaching you anything new. I'm just tidying up the loose ends. We just want to make sure that everybody who took the control elective will go through one exercise of doing these kind of things. Okay? You might have already done this in your other courses, in your project, okay, in your DIP, or maybe you're doing it now in your final project. Consider yourself lucky. Okay? All right? I just want to make sure that everybody who took control elective has a first-hand experience doing this, so that when you go out to work, when you attend a job interview, when the interviewer asks, oh, control elective, who's your professor? Professor Ling, Professor John Chan. Okay, so what do? Do you know how to use a microcontroller to do this? At least you say yes. All right, do you have a first-hand experience? You say yes. All right, that's the purpose. Just want to make sure, so this is the outline. This is what is in store for you. Sometimes John Chan and sometimes I go first, he go first, I go second. So X to me, for you, will be 8. This is week 8. All right, next week is X plus 1, X plus 2. So this week, we will, so microcontrollers, what controllers do we use? I need my stuff. So we are going to use a Arduino, the simplest Arduino. Yeah. All right. Okay. So some of you might have used this before. Doesn't matter. I don't assume any prior knowledge. I assume minimum prior knowledge. The purpose of this course is not to make you an expert with this device. It's not to make you an expert in programming this device. Okay, we just use this. So we will go through what is needed for this to implement a microcontroller basis. All right. So there are four very simple labs just to make sure that you can then program it. You're familiar with the tools, and then you can do the rest of the stuff. Okay. So report and assessment. Do you know how this course is being assessed, or how are you assessed for this course? What did Professor John do to you?
Just get the result.
Get the result. Okay. So we'll discuss about this later as we go along. Yeah. That's why there's no detail. We will fill out the blank as we go along. You must now start thinking. Just make sure that everybody is on the same page. I'm sure you know about this. As a course, 50% lab work, 50% the final paper. All right? Okay? And then, of course, that 50% lab work is shared between John and myself. So you will have 25%. Right now, half of the 50. Okay? So the maximum marks you can get from Professor John for the lab work is 25. For me, it's 25. And then there is a paper. According to my calendar, is this. Please never believe me. You also always check. And for that paper, if it is a 100 marks paper, Professor John's part is 60%. My part 40%. Okay, is that clear? Okay, then this is the board. So we just leave it here. So now let's go back to the objective. Let's discuss very quickly the first bullet point. Discuss. The way I run this course or this class is, I don't know how John ran the class with you. He gave a lecture and you just listen. No, I'm not going to give a lecture. I discuss. All right, let's construct your own understanding. All right. So first bullet. What are the key components needed to introduce a microcontroller basis? Here's the question. So let's discuss and then form the knowledge. Again, this is the way I do this course compared to other courses where I will give lectures, but this because I'm tidying up the loose ends. All the knowledge you have already. I just want to draw it out from you, and then we form this. So I'm not printing any notes. No notes required. So from the terminology of control, we always use block diagram, right? This is your plant, the terminology, plant. In your case, maybe it is your DC-DC converter. All right? Okay? And then you want to close a loop. This is your controller. You want to close a loop, correct? Why do we want to close a loop? And no recording, no picture taking whatsoever. Okay? Hello? And you should not. And I do it for purpose. Because if you record, you picture take, it's not inside here. Right? Because look, in your handphone you have how many pictures? Do you know what pictures you have? You don't know. Because you always think it's there. No, I want you to make sure that in contract it's there. No need to take notes. Just like me. Okay? So why do we do feedback? You learned this before. Why do we do feedback? Stabilize the system, very good. Stabilize. So, alright? What else? You see? You see, that's the point. You have lecture notes, and that is not yours. Okay? The whole purpose of feedback is control the parameter. What is the parameter? So what we say is, we want to have feedback because you don't have perfect information. That's uncertainty. Maybe you don't use the word uncertainty, you use noise. For students, everything is noise. Everything you don't understand is called noise. Alright, but the thing in control is you want to do feedback because you don't have perfect information, uncertainty. Right? If I have perfect information, I can close my eye and then walk. No feedback, yeah? Open loop. I close my eye and walk. But then you can stick out your leg, then I will fall. I don't have perfect information. Alright? A very simple thing is this. So this is a plant. Plant has a gain K. You have your controller. Right? If you know exactly what this K is, this is your output. You want your output to be equals to your set point. What should you do with this? U equals to W divided by K, correct? Okay, perfect. But the whole trouble is that you don't have perfect information. Okay? It may be... You learned this before? Do I need to go through this with you? Huh? Do I need to go through with you? You learned this before? No, means what? Yeah, you don't take control, okay? But you learned this before or not? Ah. Have lah, sure have one. It's just you didn't think about it this way. That's why my purpose is, as I say, I'm not teaching you something new. I'm tidying up the loose ends. You learned this before. It's just you may not realize it. Okay, so suppose do we have another color? Okay, one. This morning I used off. Suppose you don't have perfect information, right? You think you're going to use it, but the actual plant is this thing. Then what are you going to get? So your Y will be W divided by K. This is your control action, right? According to the block diagram, the output will be equals to K plus delta K times U, correct or not? Yeah? But then, when you design your controller, you think, you don't have perfect information, you think that the plant is K. So, your actual output will be okay? So if K is small, then that's good. Yeah? If delta K is large, then that's no good. Okay? So another situation is even if this is 0, you will have so-called disturbance, right? Just now somebody said disturbance, noise. Huh? So according to this block diagram, Y will be this plus this. Correct or not? Okay? Then your output will be okay? So if D is 0, and there's no delta K, then you're perfect. But how can closed loop solve the problem? How can closed loop solve the problem? You close the loop, right? You want W, you want output to follow this. So now you work out the output. So Y is equal to K times C, 1. Okay. Let's work out the U first, huh? So U is equal to C. Okay, anyway. If I choose C to be this, just now I choose C to be this, correct now? Yeah? Do you follow? So now we can work out y is equal, so we can work out the closed system, right? This is everything all in. This is 1 over k times k plus delta k over 1 plus 1 over k. Alright? And that is w. And then the d is 1 over 1 plus 1 over k. Right? This is what your close to output is. So now can you see? This is mathematics. I teach mathematics, yeah? And this is just algebra, not even math. So if, for the ideal situation, delta k equals to 0, d equals to 0, you have y equals to w. Am I not? Huh? Agree, yeah? Can I? Okay? If you choose, let's see, if you choose k, what should you choose? Okay, so now if you make this, let's do the algebra. If I multiply here, this becomes this. If I multiply this. Agree? 1 over k, I just multiply k. Alright, so now I simplify. Something is not right. Huh? So let's do it one more time. Huh? Okay, I think this is easier. So now the whole purpose of doing feedback is you want y to be w, which means you want this to be 1, this to be 0. Okay? So how do you make this? How do you make this possible? In the face of uncertainty, in the face of you want the real plan is this, and there is D, which means the real plan is this. So how should you choose your control? See, with open loop. Now with feedback, this is open loop. Open loop is like this. Y is equals to C times K times. Open loop is just open loop is just K times U plus D, right? And then you choose U is equals to W over C or K. Okay? I mean you can choose C. Alright? And so now suppose in the real world, this is delta. So if in the real world, this is open loop, agree? This is open loop. Okay, you have chosen this is your controller. You choose your controller to be this divided by so that in the real world you get. So if delta k is 0, d is 0, you have perfect information, y is equal to z. If you have delta k, then y is not equal to z. Alright? Now here, you can choose c so that this is approximately equal to 1 by just saying c times k is very much greater than 1. This will be like going to 0. So this is the purpose of feedback, to reduce the uncertainty. Alright, so now we want to close the loop. Now this is your DC-DC converter. What is the first question you, or for the first bullet, what are the key components that you need to implement this closed loop system? Bear in mind that this is a microcontroller. What do you need to be able to close this loop? You will need to bring information into the system, right? Huh? Yes? You need to bring the information into the system, and usually you studied this before, right? So this is the analog world. This is the digital world, right? And let's take for example your DC-DC converter. What's the output? Is your voltage. How do you bring this into the microcontroller?
ADC.
You need an ADC. You need this component. All right. So what are the possible sensors or measurements that you can encounter?
Temperature.
Temperature. So temperature is a what? Temperature is a what?
So what?
Temperature is a physical quantity.
Oh.
All right. How do you bring temperature into? How do you bring this information into here? You need a sensor. You need a transducer. So sensor transducer is something that will convert a physical quantity into some signal. And where electrical engineering is in some electrical signals, voltage, current. So if the voltage or current is, and so you convert this. You can read the voltage, and from there, because you have a mapping of this number correspond to this temperature, then you can bring this information into the system. Then you can do something. All right, that's the point. So other than voltage, current, what else? What kind of signal will you encounter?
Humidity.
Huh? Humidity. Okay, so humidity. So how do you measure humidity? Use a humidity sensor. Okay, and then that sensor.
Converts to meter.
That sensor give you what?
Meter values 1 to 0 to 1 over 3.
That sensor give you this.
Okay.
So
Sorry?
the humidity sensor give you direct. The humidity sensor give you what?
Meter values.
Digital value. So if it's a digital value, then how do you bring this into here? How do you bring that information into here? So you say you measure humidity, right? You have a humidity transducer that convert the physical property to some value, 0 to 1023. I suppose 0 corresponds to 0% humidity, 1023 corresponds to 100% humidity. How do you bring this number into here?
Digital input.
Digital input. Okay? So it depends on what you have. Either I2C, either digital input, if this is 10 bit, your 10 bit, and then you do the interfaces and so on. Alright? Okay? So this is not what I'm driving at. So the whole point is, yes, very good. The whole point is it actually, you just have to ask, I think you know about this, what is the interface that's required? I think I'm doing more fundamental than this. This is the basic. So you could also have a temperature sensor that give you direct this, and then you just connect it as I2C. Or now, but in my generation, we don't have such things. In your generation, maybe you don't need I2C at all. You use Bluetooth. You use internet. Okay? So the whole thing is different. So the whole point is still the same. How do you bring information in? So let's restrict ourselves to just the conventional one, a microcontroller. We are not going to use Bluetooth or this. Okay? So another typical situation that you will encounter is speed. How do you measure speed? Don't tell me it's a speed sensor. How do you measure speed? What's a typical situation where you need to measure speed? Of rotation of your motor shaft. How do you measure that? Tachometer. Have you heard of tachometer? Okay, so it give you voltage or whatever. What are there? Another one? Encoder. All right. So encoder is some dish that you shine light through it, and then here, what you do? How does the encoder measure speed? Pulses, right? So you look at the pulses. You count the number of pulses per unit time. Then you can kind of deduce what is the speed. Then, what kind of interface do you need? You need some digital input, which is like an up-down counter, alright? Okay? Alright? So these are the key components. Then let's talk about this part. So this is the digital world, this is the analog world. So depending on how you want to send the information out, then there will be the reverse, digital to analog converter. Or, so you have your digital to analog converter, you have your digital output, you have your digital input. Alright, these are the basic things. Okay, I don't go into the I2 square, don't know what, Bluetooth, and so on. Alright, so what is the difference between a microprocessor and a microcontroller? You took microprocessor course, right? So why do we say this is microcontroller? Why do we say that one is a microprocessor? Don't know. You know, you should know. Your brother will telepathy you. There's a microprocessor, right? That is a computational unit. And then for this kind of work, because there's this kind of work, the chip company will produce this chip that has a microprocessor and has a necessary component, like your ADC, like your PW. Just now we didn't say about PWM generator, like your timer or your counter, and then you put all this as a package and you call this microcontroller for convenience, so that you can just use it. You don't get a chip here to do this kind of work. Because if you get a chip here to do this kind of work, you have to build a big board. Alright? Okay, so these are the typical, so I finished that, So what are the key components you need? You need the interfaces. The interfaces are DAC, your PWM, your ADC, your digital input, your digital output. Okay? No need those, Alright. Now with these tools, this one. So we need to know how to use this. So in this Arduino, you have all these components. Alright, so that's why in your lab sheet, we again, I'm not training you to be an expert in this. You just need to know how to use the ADC module on here, how to generate the pulse width modulation, and that's all. And then how to time the loops. Don't do some simple programming. Okay? So this is what you do for today. And so now I want to All right, so the lab sheet is all loaded onto your computer. Some of you might already have seen it. There's a demo program, so you just go through that. The whole purpose is to let you familiarize with the tools, so that you know, oh, you use this, this is how you use the editor to compile the program. This is how you load the program onto the microcontroller. This is how you see what's happening. Okay, so we finished that. Maybe I just quickly show you what is this. All right. So for example, ADC. Now, you will see that in the lab sheet and your code is slightly different. All right, because in the lab sheet it is the older version of the code where we review or we kind of do very low level programming, all the details of how to set the register and so on and so forth. This one, we have kind of used an object-oriented approach to hide the details. So what you need to do is just use the function. All right, we'll see it later. So this one is not so interesting. This is simple. I think it's the same as the code. We don't need to hide the details. Oh, there's not much detail. So the Arduino basically is this way. There are two main functions: setup and loop. So these are the keywords. So when you compile it, what happens is that when you load the program, the setup function will be run once. So it's like initialize. And then the loop function will kind of execute the statements in a sequential manner and then loop back. Okay, so this is so if you look at this program, you will be able to kind of understand what the microcontroller will be doing. So initialize the serial port at 9600 baud rate, and then you read from the analog channel A0 and read it into a variable, and from there you print out the value. All right, print out the value and then delay for 100 milliseconds and repeat. So what's happening will be on your monitor through the serial interface. You'll be able to see those values that is read by the microcontrollers. So this is how you do the ADC. Okay, this one is more perhaps more interesting. So this, if you look at the code, maybe there are a lot of details. But now we hide it in the library. You don't have to know the details, but if you're interested in the details, the details codes are all there. So to do this, to run a PWM, we have two types. One is PWM1, one is PWM2. The difference are highlighted here. If you use a PWM1 type, then the output pin is at P9 and P10. The frequency of the PWM is adjustable. Okay? Alright, here is set to 10 kilohertz. If you use the PWM2 pin, the output pin is at P3 or P11. The frequency is fixed. That's the simplest one. Alright, otherwise, the usage is the same. That's called object-oriented programming. Yeah? You just change the duty cycle. Change the duty cycle. You don't have to know the details. But if you're interested in the details, you can look at the library. I mean, our library, which is in your directory. Okay. So what happens? So you can imagine what does the code do? Again, it sets it up, set up all the necessary register, either to generate PWM on pin 3 or P11, or when you use this, it will generate PWM signals from pin 9 and pin 10. Okay, and this set the frequency. This one is fixed at 7 kilohertz. And then what happens? We just keep on saying generate this PWM and this, and then repeat. So you can imagine with this kind of basic tools, you can begin to write simple program to do what you want to do. Adjust the frequency, and the next one. So you can begin to do this kind of thing. This is the old code, actually. So you can begin to do this kind of things. Just imagine, read the analog channel, and then forget about this. You think of it as set PWM value according to the analog channel. So you can imagine as an analog, as your voltage change, your duty cycle will change. Okay, that's the first step towards closing the loop. All right. Now the next part. Very often, you would want to time. You write a piece of code. You would like to time how fast or how much time it takes from this line to this line. How to do the timing? How would you do the timing? You use a stopwatch, right? No? You use a timer. So you write C program, huh? You use a timer. I don't know how you will time the piece of code.
Import time.
Huh?
Import time.
Import time. Yeah. Okay. So you do Java or the whatever. Now what is the in thing? Whatever you bring in the library that has a timer function, you basically do a software stopwatch. Yeah. Software stopwatch. Here you say, oh, start. Conceptually, it's like that. Start, stop, and then you look at the time difference. You know what is this. Okay. Now, we are the poor engineers. Okay, we don't have these tools. Then how? I don't have library. I only have microcontroller, the rudimentary C program. I cannot import timer. How?
It's using its clock.
Hmm?
Using its clock.
What clock?
The microcontroller's clock.
I don't know how to use a clock. I mean, how to use a clock? You see, that's why. Okay, maybe this is why we have a generation gap. When I was brought up, there's no such thing as import timer. Okay, you basically set register. Or now everything is given to you, but I still want to go back to this. Suppose now you use timer and so on. These are the tools, the concept. The thing is that then you have to read the manual how to use the timer. Okay? Or someone might say use interrupt. How to use the interrupt. Okay? The question then I'll pose to you is, okay, so if you use this timer, you use this interrupt, what is the timing resolution that you can get? Do you know? When you have to read the user manual and then you give up. Alright? Suppose. So what is the alternative? Now we are in the lab. We have a microcontroller. We have digital input pin, you have digital output pin, you have PWM, you have all this kind of thing. So how can you do the same thing? Huh? Oscilloscope. How to use the oscilloscope to do this?
Set a pin to high.
Yeah, very good. Set the pin. Alright, you have digital output pin, right? You can do the similar concept by saying set a particular pin to high. Digital output. That's the instruction. Okay? So these are the basic instructions that you need to know. Or I put it the other way. Whenever you have a project, let's say out in the outside world, somebody will give you a microcontroller from whatever company. Do you have to read through the manual? No need. Or you have to read through the manual, but what are the essential information you should get? These few things. How to set a pin high, how to set a pin low, how to read a digital pin, how to use the ADC, how to use the PWM. Finish. Enough. Okay? Then you can quickly do your work and then get a raise from the manager and move on. Alright? That's how I want to impress upon you in this class. Okay? So you have this and you run this, and because this is going round and round, so what do you expect on your oscilloscope screen? If you monitor this pin, you will see this, right? High, low, high, low, high, low. Because it runs round and round, it gives you a periodic signal. You use the scope, it's very stable. And then you can take your time and measure. Okay? No need to read the manual, you know exactly what is it. Okay? This is one of the job interview questions. If you come to this, alright? You say, alright? then you can answer this. You can get a job. Okay, so here is a simple demo program. You write to pin 9. I mean pin X, whatever it is. Not important. Yeah. High, and then delay. Delay is a built-in function of the compiler. In this case, we give you a 1 millisecond delay, and then you set it to low, and then you delay for 3 milliseconds, and then repeat. So you can imagine what you expect to see on the scope, and then you confirm it. That's the purpose of bringing you into the lab. You see with your own eye. This is called first-hand experience. Okay? And then you should use the scope and measure it. And then kind of have confidence or kind of check that, yeah, it does what it's supposed to do. It gives you 1 millisecond delay. Or 1 millisecond and plus 1 nanosecond delay. So that you have an idea. Alright? That's what I mean by first-hand experience. Okay, so this is all for the demo lab or for knowing the tools, and this is all you need for this class. Okay, I don't expect to train you to be an expert. Okay, so once you have these basic tools, you can do quite a lot of things already. Now, next, I want to talk about some open loop tests, some idea, or some, or revise with you some thinking how to. So imagine that you graduated, you landed up in a job, huh? All right. You say you are control elective student. Your professor is John Chan and Ling. Oh, very good. You end up a job. And then the first day of job, you get an assignment. Use XYZ microcontroller. Close the loop. So, I give you this plan. Your manager give you this plan. Say close the loop. What will be the first question you will ask, so that you can carry out the task? How about you? No, I thought I see a lot of light bulb there. No? How about you? Anyone? Open loop test. No. What is the question you want? What do you mean by open loop test? Open loop test.
That's the output.
Okay, never mind. So where's my duster? I have a habit of.
On the floor.
Okay, so this one can erase now. You see, you do with Professor John Chan. This is your DC-DC converter. Right? Now, you get an assignment, you say, this is something. Close the loop. Alright? The first question at least you should ask yourself is, what's the purpose? What's the purpose of closing the loop? What is the controller supposed to do? Right? So your DC-DC converter basically is, you want to maintain the output voltage to be at some set point. You want to have a controller that closes the loop to maintain the output voltage at some set point. So with this understanding, what question should you ask yourself? How to kind of close it? How to design this? With Professor John Chan, what do? You do a lot of calculation now, right? Correct? This is what I want to impress on you. So you do a lot of calculation because it's with John. Because it gives you the transfer function. Yes or no? Right? Correct? It gives you the specific, it gives you the transfer function. Okay? Imagine you end up with something, nobody is going to give you a transfer function. This is, in the university, we give you a transfer function. Tutorial question, we give you a transfer function. So what would be the, as a, you now wear the engineer's hat, what question would you ask? How to do control? You will ask, what is the input and output signal? Correct? I think I'm sure all of you actually had in mind this. It's just you are too shy to say this. Okay? But I say this is not enough. What do you mean? So in your case, what is the input and output signal? What's the input signal for your DC-DC converter? Huh? DC voltage. What's the input signal for? Is it DC voltage? Yes. DC voltage. This is output. I think everybody will agree. It's output voltage. How about you? You're the yeah. You're the power student. Don't need. Never. That's why I like to ask
Why
you.
you ask me a post?
Yes, because you're not corrupted by the control yet. Ah. Huh? DC? Are you sure? You see, you do control, you have to ask this question. What do you change in the input to affect the output, isn't it?
The reference voltage.
Okay? No, you don't change it. That's where everything goes wrong, really. This is open loop. Open loop.
Okay.
You have something. If you want to control something, you need to know the basic information. What is it? What can you adjust so that the output can adjust, right? Can change. Right now? This is a basic question you need to ask. It's not about control, it's about basic question. I'm now in this class. I want to change your learning behavior. I need to ask, what do I have to do in order to change your learning behavior? I said tutorial question, right? Okay. Alright, so your DC-DC converter, what do you have to do to change the output? Huh? Function gen. You see, that's where everything goes wrong. You change the duty cycle of the PWM signal, alright? Agree? Okay, so I hope now you agree with me, right? You change the duty cycle of the PWM signal. So that then you can close the loop one. Alright? Because with John Chan, you focus on design, because he gives you everything already. Catch up the circuit, calculate the inductance value, then close the loop. Then you don't even know DC-DC converter as a block by itself, how it operates. I mean, you know, but you forgot that. Okay? Alright? So I'm trying to get to this point. So this is your PWM duty cycle. The basic of this. Yeah? You build a PWM generator. You look at the circuit now. You essentially change the duty cycle depending on the era. Okay? Alright? But then the whole point of closing the loop is gone. Okay, so with this now in mind, clear. The first question you ask yourself for open loop test is find out the input-output relationship. Yeah? So what do you have to change the output? So now we agree that you need to change the duty cycle of the PWM. So because look, in your tutorial is always this. Essentially now I ask you this question. So what is Y and what is U? So Y is very obvious. Y is V naught. Output voltage. U is duty cycle. Okay? Alright. So with this in mind, then you will want to find out what we call the static input output map. Which means this is Y, this is U, this is a static, this is a zero frequency. I think you are familiar with this. You want to know at 10% duty cycle, what is the voltage? Yeah? Okay. Right? Okay? Okay? So this is, and this will tell you quite a lot of things. This what we call. Our approach is what we call the black box. I don't have to know the circuit detail. I treat it as a black box. Do you agree? I mean, with this kind of approach, I don't have to know. You can give me whatever things I don't have to know. All right? I don't have to know the details. I just need to take it. I just need to know the transfer function. All right? So the other approach is you need to open up, like what you did with Professor John. You look at the circuit, derive the transfer function, do a lot of calculation, and then do the compensator. Here, this is a black box. Okay, so suppose you did the experiments and you get this data, and then without thinking, you just draw a line. Okay, so what does this line tell you? What does this line tell you?
Linear response.
Linear response. What do you mean by that?
It means the output respond linearly.
Okay. You see, this is a transfer function, right? Just make it more concrete. Suppose it is a first order transfer function. What does this line tell you? Or what does the gradient of this line tell you? The gain, the static gain, K. Alright? So if you have a line like this, then you can say that, yeah, the plant is so-called linear, or in other words, the gain is the same throughout. Well, you may collect data and then you may get a line like this. Then you say, oh, there is a gain in this operating range, which is different from the gain in this operating range, the static gain. Okay? And that will influence your so-called controller design, right? You will have a more clever design. Now it's software, right? You will write the software. Oh, if you're operating here, then I will use this parameter. If you're operating here, I will do this. This is what the industrial say, intelligent control. Or fuzzy logic, neural network, whatever it is. Okay? Alright? So this is what I mean by the open loop test, static math, linearity. Okay? Alright? So there are these kind of considerations. There's no math involved. I'm just wanting to kind of tidy up the loose end. You learned all this before. You learned a lot of maths and a lot of analysis. I just want to present a situation to you. Now you have lab. Now you have your things. What do you look for? Okay? Where the engineers can. And tie what you learn with what you do in practice. Okay, so suppose we make the assumption that this, your DC-DC converter, can be described by this first order system. Then we can do a step test, right? We can do a step test. And then you expect this. Have you seen the step response for your DC-DC converter? No, right? No, right? You'll do this without needing to look at the step response, right? Okay? So again, I'm talking in general. So to do this kind of test, what are the assumptions? To do an open loop test, what is the most important assumption? The plant is open loop stable. If the plant is not open loop stable, you cannot do. Alright? It's safe. So before you carry out any test, you must make sure that it is doable, it is safe to do. Okay? And by the fact that you use transfer function, you are implicitly assume linearity. Okay? Which means when you do step test, what should you be kind of concerned about? Because any plant, any real world plant will have, it's not perfect, will have non-linear effect. Yeah? The Earth is not flat. Huh? But if you look at here, Singapore is flat. Okay? Alright? So if you do step test from 0 to 100%, most likely you will see it doesn't look like a first order response. Okay? But if you do from maybe 10% to 20% or even 15%, you'll most likely see a linear response. Okay? Alright? So I want you to think about these kind of issues, and then for your open loop test, do these kind of things. Alright. So now we can talk about right? What happened? Okay, so this is the thing. I discussed all this. So now I want to be more clear about your open loop test and what you can do, what you should record. You have a logbook, right? I suppose. No. What do you do with Professor John Chan? Where's the logbook? And then you have your logbook. Huh? You have to make record basically. You come to the lab. I don't care what you do. You bring a piece of paper, you bring a book, you bring a handphone, you whatever, but you keep record. Okay? So just now when we discussed, when you do open loop test, what I would like you to do is to keep record. Okay? What I would like you to do is to keep record. So you carry out the input-output static map. You will keep record. You will produce this map. Yeah? Okay? And show it to me. Demo. This is called the demo assessment. Alright? I say assessment. Everybody pay attention. Alright? Okay? We'll do the step test. Just now we discussed, right? Step test. There are various ways, various considerations to do the step test. Where do you start? Where do you end? Means how big is the step? Okay? And I want to again let you see for yourself whether this is the case or not. I'm talking in general, but so we use this as a case study for you to see for yourself. So you should try to do step tests at different operating conditions, different step size. Huh? Then you see for yourself, you record, you draw it out, or you take a picture. What is the step response? Does it look like a first order? And then you can estimate the time constant. Or does it look like this? Then obviously this is not the first order assumption is not a good assumption. Okay? Alright? So you see for yourself. And then you show me. Okay? So is that clear? Open loop test. Do a static, do a step test. Of course, if you are adventurous, you can do a frequency response. You can find the body plot of this. Okay? Alright, alright. In principle, you can do. I'm not asking you to do, I'm saying if you are adventurous. So let's discuss. In principle, how are you going to use the tools here to find out the frequency response? Now I'm trying to tie up what you learn. Huh? How? Did your brother tell you? Huh? How to find out the frequency response? How to find out frequency response? So in theory, what is the frequency response? How do you work out frequency response? Like that, right? You send in sine wave, you look at the sine wave output. Huh? You make sure that the amplitude is small enough so that this also is a sine wave. Linearity assumption. So in principle, to work out frequency response is you send in a sine wave at a particular frequency, look at the gain, you get a point at this frequency. You look at the phase difference, you get another point. That's your monitor plot, that's your phase plot. And then you change the frequency, you get this. This is a body plot. Okay, so in principle you can do a crude frequency response, but it will be too hard because then you have to generate sine wave. Now, generate step test is easier. So in your case, how do you generate a step test? You just set PWM to 30%, let it stay for a while, everything is settled down very fast. You know how your DC-DC converter works, right? Everything happens almost instantaneously. Half a second. Hold it there, half a second, change 50%. Hold it there, half a second, you will see this. Of course, you have to zoom in to see the transient, depending on the time scale. Alright? Okay? Okay? So you do this. Now, when you do the static test, you can imagine you are going to carry out a series of a few experiments to determine these points. Now, your program might look something like that. This is why we do the demo program. You set 10% duty cycle. And then just delay, and then just let it run. And then you look at the monitor, oh, this number, record, you got a point. Then you go to the program, set 20%. Oh, this number, record this point. Okay? Then after a while, you find this is very boring. Yeah? Hey, why don't I write a simple program to automate this process? Can you imagine yourself doing this? So this is what I suggest to do. You can, right? You can write a simple program, just a simple for loop. Say, oh, okay, so the first round, 10%. Second round, 20%. Now you can imagine, right? It's more interesting. You just press a button, wait, everything all around. Alright? Okay? Now if you write this program and run it this way, so now you write a little program that does this. So you imagine your scope, this is your time. The scope, you monitor the output. Alright? So the first round, 10%, the output will be here. Let's say you hold it for 1 second. And then the second round, 20%, the output will be here. And then if you write a program, then just cycle through. Step up and step down. You'll see this. Okay? So by this one look, it tells you quite a lot of things. It tells you, so when you look at this, assuming that the step size is regular, and this is also regular, you will know that you get this. Okay? If you get this sort of things, especially, right? As it's near to the VCC voltage, your gain is smaller. You know that you won't get this. You will get this. Okay? So this is a very useful things to do because whenever you have doubt, you can always just press a button and run it again and see whether anything changed or not, rather than manually repeat. I would like you to do this. Okay? So I would like you to write a little program to do this. Take a picture of what you get. Then of course from here you can create this. Okay? I'll let you to do this. So you select what I usually want to do is small, medium, large. Small step, medium step, large step. Okay? At different operating conditions. Whether you operate here, here, or here. So the whole purpose is So we're not doing a lot of calculation, but I just want you to go through the experience of
So how many sets will you do? Up to you.
how do you small, medium, large, 3 points. Just to give you an expression, just to give you an example. So we're not going to, just so that you know how your DC-DC converter behaves. Okay? There's not much calculation. My part is not like John Chan's part. You do a lot of design calculation. I think you have enough. My part is to focus on letting you do some hands-on work. Alright? Okay? So you do this. So I would advise you to do this. You know your plant, and then after a few choices, you will have decided what will be interesting to show me. Huh? You small, medium, oh you show, oh then here is like that. If you do this, then it will become like that. So this kind of thing is no good. Alright? Something like that. So that I can close the loop. Alright? Okay? So this. Okay? 2 pages enough? Right, 2 pages. Since you work in pairs, so each pair give me 2 pages.
This one, is it this week or next week?
Next week.
Oh.
X plus 1, X plus 1, X plus 2. Okay?
Yeah, it's not next week though.
So I do the briefing now.
Okay.
This week is X.
So next week.
Very fast. I mean, it takes half a lap. If you are very familiar, it takes 1 hour or
So
even
you can
30
do it
minutes
next
to
week
finish
onwards.
this. If you finish early, you can do
Then next week.
open loop test. Well, no. If you manage to finish everything, I'm sure you cannot finish one. Okay? Because now it's what? Now it's 2:46 already. I'm sure you cannot finish the open loop test. Alright? So we have next week what I call the independent studies. I already set the assignment. You come, I know come. Next week.
Oh.
Next week you are expected to be here. The TA will be here helping you. I don't come. Because
Can you
I'm
get Prof. John Chan to come?
you can invite him to come, but okay, usually I will be here, but next week I'm asked to be somewhere not in Singapore, so I cannot come. Alright? So I set it up this way. Next week you can do, then X plus 1 you do in the lab, you have all the time to do it properly. When I come back, X plus 2, I'll go around and check your work and so-called assess your work, close the loop. Okay? Is that clear? Sorry?
The 2 page is submit on the X plus 2 ah.
Yes, X plus 2. X plus 1, I'm not here.
So you want hard copy or you want soft copy?
Hard copy. I don't want soft copy. Soft copy means you don't know where is it. Okay?
So the step test and the static map, you can do the same thing.
Step test, static map, different thing, right? This is called the static map. Okay, so I would like to see the information. What information do I want to see? This one. Your little program, how you do it. Okay. Now, once with this, you'll be able to generate this, right? Correct? And then you can, it's up to you. I only require you to do this. This one, you can do it manually, or you can have a clever way. It's up to you. And you can impress me. Okay? But I want to see this table in the sense that I want to see an understanding of doing a step test for different step size. It will lead to different behavior in general, but you may not see it, never mind. Okay, try to look for this kind of thing. Try to show evidence of this kind of thing. Okay? maybe you'll say that, oh, this is the first order is not a good assumption. Because your converter is like that. Have you seen how your converter behaves? No, right? Okay. I think that's all I have for first and the second bullet. Any questions before I let you go and do the practical work? And then of course the TA will be around, and help you. Okay? So before you go away, let me remind you one more thing. I think that's very important. Okay, so here, just now I already said this. Okay, so when you don't see the expected output, you don't see the PWM signal, ask yourself this question: which type are you using? Are you looking at the right pin? Okay, all right. And you might want to, when you do those tests, you might want to also investigate, because you do a lot of calculation with John Chan, right? Different PWM frequency will give you different, there are design considerations. You see whether it is actually happening or not. And then you may want to find out what is the ability of this microcontroller. What kind of frequency can you generate? Here I say 10K. What's the maximum frequency? Okay, not megahertz. Okay, now what is it? And here you might want to find out what is the maximum delay that you can generate. Let's have a discussion. So why is there a maximum delay? Why is it not infinity? I think we must have this kind of understanding, right? We are EE students. Just imagine how is the delay implemented? Whether hardware, software, or whatever, it's basically a counter, right? You just count. Okay, so if there's a counter, there's always a maximum value. Whether you use a 32-bit integer, 4-bit integer, 128-bit integer. Okay? Alright, so you might want to test this one out. See for yourself. That's what I mean. See for yourself. So if you set 1, is it really 1 millisecond? 2, until when it breaks down. Until when there is an overflow of the counter, it will break down. So what is that value? Suppose that value is, I don't know, let's for simplicity, 1000. Okay? So if you set 1001, what do you expect the delay to be? So you ask yourself this question, and then you confirm it by doing experiments. So then you become more confident, you know what's happening. That's what I want to drive at. You're in the lab, that's why we bring you to the lab. Then you can carry out experiments to see for yourself. That's called lifelong learning. Okay. Alright. Okay. Another thing very important. This is the most important part. I don't know how your circuit looks like, but in principle, it should be something like that, right? There's a DC-DC converter, there is an op-amp, and here is the PWM input, and then here is where John Chan gives you the solution. This is how you implement the compensator, and then you hook up the compensator, and the compensator somehow magically generates the required PWM with the required duty cycles. Okay? So part 2 is essentially replacing this part, your compensator, throw your compensator away, now do the microcontroller. Okay, so if you imagine there's a microcontroller, you will connect the output to the ADC input. You will connect the PWM pin to here. Okay? Alright, now very important. The ADC input can only take 0 to 5 volts. Means what? Your DC-DC converter, in the ideal case, actually go from 0 to VCC. Your VCC is 10 volts. So if you connect it, my Arduino is going to be what? McDonald's nuggets. Correct? You know what I mean? You're going to fry my Arduino. So please, I don't want McDonald's nugget. I want Arduino. So what do? Lower down the DC? No lah. Your converter circuit is already there. Lower down like that. This is your V out. Find two identical resistor. Tap from here. Okay? So if this is maximum 10, what is this? 5, huh?